Hello, hello everyone. So welcome to today's course. Week 5. We've actually covered quite a lot of things until now. I will give a brief recap, but I wanted to know, like, since we don't have any tutorials and so forth, I'm not really sure how all of you are doing, coping with the material. So there's an online questionnaire that you can fill out voluntarily and anonymously, obviously, on Canvas. I think I uploaded it yesterday or the day before, I don't remember, where you can give tips or feedback or any comments, positive, negative, what you like about this course, what could be better. So for instance, a trivial thing a student mentioned I shouldn't write in yellow, because it's not well readable, so that would be a simple tip. Another student mentioned that I should give a bit more intuition to make it easier to follow beforehand where this whole story is evolving. So I'm trying to do that. But yeah, any kind of tips, but keep in mind the level of math is sort of fixed. It's a course in the math department. The curriculum is just what it is. So the math level, yeah, we cannot do anything about this really. But any other tips would be greatly appreciated. So, week 5. As I mentioned before, we have done many things so far in this course. We started from, well, the very, very basics, like what is replication, how replication leads to prices, why the prices are fair, no arbitrage. We've considered the binomial model. We've introduced stochastic analysis, and finally last week I introduced the famous Black-Scholes model. We spent a lot of time deriving the Black-Scholes PDE, so the formula for option pricing, in the Black-Scholes model. I would give a 5 minutes recap on the basic, on the core ideas. But that's what we've done last time. And what we're going to do this week and also in the following weeks is study the numerical aspects. So we've derived this equation, and what we want to do with this is, well, get some concrete prices out of this equation, out of this framework. And this is what we're going to be doing for the next few weeks. Later on, when Semi will take over, you will again see the Black-Scholes model and the Black-Scholes framework, just in different forms, with different goals, with different modifications. So this equation, yeah, so by the way, Black-Scholes is really important. It's not just a toy model. So you've really come across to a simple but really practical model that is actually used, and modifications thereof, but that are really built on Black-Scholes intuition and modeling. And this equation, also really beyond finance or quant finance, if you study courses in PDEs or in physics, it actually comes up as an example. Yeah, so this is also what we're going to be doing today, actually. Solve it numerically using PDE methods, classical PDE methods. So today they could be a lecture I could be giving in the 80s. There's, that's still on, right? Yeah, so it's old school stuff today. Later on you will see a bit more modern approach, and I will also explain various pros and cons of all of these approaches, well, throughout the way, even today. And in fact, if you have studied this exercise sheet, I think 3, where you've calculated prices and by multi-period binomial model, you've seen something very similar as the algorithms that we will encounter today. Yeah? Similar spirit, of course, not the same algorithms. Okay, so now why are we interested in solving this PDE? Just to recap. To get any possible confusion out of your way. If you Google Black-Scholes prices, you will immediately find many pages that give you explicit formulas, yeah, for Black-Scholes prices. That's true, but these formulas are highly restrictive, so they are really only applying for call or put options, yeah, not for general options. And so our task is, as I mentioned before, like they're rarely explicit formulas. This is one of the cases. In general, there's no explicit formula. You need to do something. You need to solve this PDE, for instance, numerically, not analytically. So that's just, so there are benchmark cases where you can, for instance, also test goodness of your approach, but not in general. Okay, so back to the Black-Scholes PDE. This was the PDE that we've derived, and to clarify, just the notation, it's always, the scenario is always, we have a function b that goes from time interval, and in this lecture today just from real line, so we have one stock, to the real line. So this is a function of two inputs. And this here denotes the derivative against, the first coordinate, and that here denotes the derivative in this coordinate. Yeah, we write it, typically it's customary to write it like derivative in S. Of course, S, if you think about as a process, that doesn't make sense. It's really the coordinate where you always put in the process. Yeah? Second, the derivative in this coordinate. Yeah? Good, so this is the PDE, and just to remind you how we derived it actually is by the replication argument. So going back to the slides from last week, the assumptions of Black-Scholes here. We have log normal dynamics, a bank account, log normal dynamics, exactly. And if we denote by VT the value of the payoff at maturity, but today at time t, so today, given that the stock price is ST, if we denote or write this down as a function, then what we were set out to do is, well, find a portfolio that consists of delta units in stock, psi units in cash, that perfectly replicates the terminal payoff. And if at every time, if we can do that, then certainly by no arbitrage argument that would be, so V0 at time 0 would be the unique fair price. And magically that was possible. Yeah? And that's really magical. And the way we derived this is by saying, well, if pi is 0 all the time, that gives us one condition, but also we can differentiate or take differentials. And, well, zero function differentiated is again 0. Yeah? So that gives us, using stochastic, maybe I'm skipping forward here. Then we could use tools from stochastic analysis. Namely, we could consider the dynamics of the price process, the value process V. Let's call it value process. So it had the Ito term, it had the Ito correction term, and we used self-financing argument to compute, without doing any like Ito calculus or anything, the evolution of the portfolio, which we call C. So this was really self-financing, so that the system is closed. Rebalancing the portfolio, I can only use what I am given at each time. And the crucial insight was now the following. I'm just going to repeat that, and then we're back to today's lecture. The only way that the dynamics are 0 is, well, if this term, both right-hand sides are equal, and the only way that could potentially be true is if this stochastic term vanishes. Because if there is really a truly random component that behaves of a much higher order of magnitude than dt, namely like square root of dt essentially, yeah, then there's really no chance that you can somehow account for it using these other terms. So that was why there's only one approach, reasonable approach left to pursue, is setting delta to be the delta hedging, so minus the derivative of v. That's exactly what is written here. Good. Okay, if you do all that, and we've done it last week, you arrive at this Black-Scholes PDE. We've discussed boundary conditions and so forth. So this is an equation for an unknown we want to solve numerically. And given the boundary conditions, this has a unique solution. And that solution is, well, contains both price and the hedging strategy, which was just the derivative, the partial derivative of this solution. Now, in order to give you a bit intuition where like all of what I'm talking today is placed and practice, I'm going to steal a slide from Semi, where he sort of gives you a bit of intuition. So typically, how this is working is as follows. So you have three components in the market. A bank, like just the real world, like whatever the prices are evolving, and a client. And the client could be like a person or an investment bank. Okay? So now what the investment bank does is they want to buy, they have some belief, they're taking risks, they had some belief that, I don't know, NVIDIA will behave in a certain way, and that's why they want to buy, say, a call option on NVIDIA with a certain strike price, to make it very simple. Yeah? So what they're doing is now they're calling an investment bank, asking how much this call option will cost, if they want to say in a year. And what the bank does is now the following. They will compute very quickly a price for which they can find exactly what we've done so far. So find a portfolio that replicates this call option. Call option, I said, yeah. Sell it to the client for, well, a bit higher price. Obviously, they want to make they're in the business of providing a service, so they want to make a bit of profit. They sell it to the client for a slightly higher number. And the terminal time when they need to, when the transaction needs to happen, they're perfectly covered. Yeah? They're not taking any risks. So there's sort of this duality of investment banks that really are there to eliminate risk, or they want to eliminate risk for themselves. Clients, hedge funds that are taking risks. That's how the market goes. And as you can see from this example, there's one important takeaway maybe. Yeah? So clearly for call options, we've seen that there's formulas. There's no need to do any fancy calculations. But typically it will not be a call option. Yeah? Maybe the client wants to buy the squared, an option that depends on a square, so pays out the square of NVIDIA or whatever. Yeah? Just an abstract, complicated formula. And so the takeaway is you need these models or the numerical implementation of these models needs to work out quite quickly. So no one will wait for days to for you to give them a price. Yeah? So when we set up these models, always keep in mind that the crucial component is not only accuracy, but also runtime. Yeah. Yeah, I think that's the main takeaway. At least I wanted to give from this slide. I'm sure Sammy would have done a better job, given that he actually works in this industry. Okay, so I think this is just again the recap. Exactly. Yeah, okay. In 2 weeks, I think, or 3 weeks, there's a break in between. But we will actually see a simulation, how these things work, how these things update with, well, simulated data, of course. But yeah, you will see, you will be able to track the portfolio, track the stock prices, and so forth. Okay, let's get started with today's lecture, actually. What we're set out to do is compute numerical solutions for our Black-Scholes PDE. So this function v, as I mentioned before, the value function, it's unknown. You only know it at time t equals capital T, so at terminal time. You have the PDE description of v, so that's a condition this unknown function needs to satisfy. It uniquely quantifies it, and you're aiming to solve for it. Now, the first thing that we're going to do today is, well, restrict ourselves to one-dimensional, well, example. What that means is that there's just one stock. So actually, we've also only covered always one stock. But in principle, you can think there could be multiple stock prices. You could have a, well, not just one stock, but an option that depends on 5 stocks, 10 stocks. Yeah. So today we will be only doing 1D for 2 reasons, actually. The first one is because it's simpler. I can write, we will have 2 dimensions, so time and space. I can draw a grid. It's harder in 3 dimensions or more dimensions, obviously. But also, I will come back to this. The downside of these methods, these really discretization PDE methods, classical methods, is that they really only work well in low-dimensional examples or low-dimensional settings. So as soon as you have many dimensions, this discretization will get out of hand. Yeah? And if you think about how many points you need to discretize an interval, it's linear in the it's like 10, say, a cube. No, what's a sheet? It's like 100. A cube is like 1,000, and so forth. So it grows exponentially with the dimension. So all of these PDE methods that we discuss here, by discretization, are really only applying low-dimensional. Later on, you will see statistical solutions for high-dimensional settings as well. Good. Okay, we start very simple with a very simple model. Forget that we're talking actually, or we're actually interested in solving PDEs. Let's start with ordinary differential equations. Or in fact, not even that, just integral equations. Yeah? Now, how would you approach such an equation? So that is just y t is just the integral of 0 to t f, capital T, f of t dt. Yeah? Now, if that has magically a closed form solution, then you're lucky. But in general, of course, if you want to compute this numerically, you need to discretize. Yeah? So what you do is, if this is just 0 to t, you have this function here. I mean, okay, you set up a grid, t1. Maybe this is t1, actually. Okay. Nope. Oh, no. Okay. Let's just leave t1 like that. You discretize. Yeah? We've seen it also before. Now for ODE, where you have a function, where you have a equation like y of t is f of y of t, y prime of t. Yeah, for some function f. The most natural thing that you can do is again the same thing, discretize. So numerical solution is, say, y tilde t. And the most natural solution that you can do is, well, y k plus 1 is just y tilde tk plus f of y tilde tk delta t, and recursively compute your approximation of the function that way. Yeah, so what you're just doing is well, what you're doing is you could view this two ways. Probably the easiest way is what is written written here. So in fact, this discrete derivative, let's call it discrete derivative for today's class, okay, is very close to the true derivative if delta t is small. I mean, the left-hand side is the limit as delta t goes to 0 from the right-hand side. Yeah. So what you can do is, well, just replace the true solution will satisfy that up to a smaller order error, or t square error. You neglect those errors and you arrive at this equation. And how that looks in a picture maybe is that should be like the exponential. Maybe here f is just the identity. Yeah. So that is the true solution, e to the t. E to the t is the only solution, which, I mean, the derivative is the function itself. And what you're doing in this discretization argument is just, you have the grid, here's one point, here's the next point, here's the next point. So essentially you're doing a linear interpolation between this point. Here the derivative is slightly higher, so you go here. The derivative is again higher, you go here, and so forth. And you can imagine, like, if you do this finer and finer, it will converge to the true solution. And what you can actually show, for instance, in this example, you can show it by hand without any deep tools, is y tilde delta t of, say, 1 minus y of 1 is of order delta t. Yeah? In this example, for instance. Yeah, you can calculate explicitly what this solution is. It will be just 1 plus delta t to the power of, well, time steps, spacings, and that's the error. Okay, and so our methods will be essentially the first method that we discuss. We will be discussing 3 different methods, and each method will have certain advantages, certain disadvantages. But the first method that we discuss is really exactly based on this idea. Yeah? This is why I spent so much time explaining this, even though I'm pretty sure many of you have seen this already. So what we are going to do, so how the picture changes for us is as follows. Remember, we have a function we have a function v that depends on t and x. And again, what we're trying to do is compute it at a discretization of the space. Now, the space will be 2-dimensional, and in order what I will do is I will write down time in this direction, and I will explain in a second why. I will write it like this. Yeah. Here I will discretize space. That's some S min, S max, and so discretize time and space. So the only points that we exist in our universe, in our discrete universe, are the the points in the grid. So these points, all of these points exist. And as min, you can think of, well, 0 or minus infinity. I mean 0 for our exponential model because prices are positive here. S max is some astronomical number that is extremely unlikely that the stock prices will ever evolve outside of there. And we've seen, like for the normal distribution, like it concentrates tightly around its mean. So if you have a stock price that's roughly 100, you have a reasonable volatility of order like a few percent, 10%, whatever. There's no, I mean, the chances of the stock price exceeding 200 are astronomically low. So you don't really care about this. Same for S-min. Right, so that's how you get the boundary points, S-min, S-max. One thing that I'm going to do in today's lecture is I'm going to always solve the forward instead of backward formulation. So I'm going to think of this reparametrization. And I'm going to, in contrast to, for instance, the binomial model, I'm going to draw it like that, meaning that time evolves in the y-axis. And the reason I'm going to do that is because that's the typical way you would consider these type of equations. Why? The answer is quite simple. And I told you, I mean, I almost told it to you before, we are back in the 80s. So that's when all of this was initiated by physicists. The Black-Scholes equation is just a reparametrized heat equation. I've, well, not proven, I mean, but the parametrization was in the lecture notes. So Black-Scholes is just heat equation. If you think about heat equation, what's the natural way of writing it? Well, I have a medium, here just this S-min to S-max. I have a distribution of heat at initial time, 0. It disperses as time progresses. So that's the picture you would look at. Yeah. You're more than welcome to write it on rotated 90 degrees or 270 degrees if you don't want to do the switch between forward and backward in time. It's of course all equivalent, but this will be the way you'd see it in most most lectures or lecture notes or books or so forth. Okay, so this is our universe. And the difference to before, maybe I'm not going to draw it, just show it to you with the pointer, is before when we considered this ODE, essentially what we had is we had one point here, somewhere, a fixed point, and in order to calculate, we could fill out this whole array just by backward induction. So for this point here, I only needed to, let's see, know this point, plug it into the derivative, compute this point. For this point, I will just use the point before and so forth. So the difference now is that this function b, in order to compute the next point, I not only need to know the point here, but also something about its first and second derivative in space. That's the difference. And the way we're going to approach it is, well, very, very natural. Oh no, this is wrong. This is okay. Okay. Yeah, the way we're going to approach it is very natural. We will first consider, well, we will replace always true derivatives with discrete derivatives in space. So yeah, for a generic function f, so f will of course later on be the function v at time tk, for instance. Yeah. But for an arbitrary function, what I can do is just write down its Taylor expansion. And that Taylor expansion tells me it tells me what. So this is maybe the function. This is my point xi. This is my point xi plus 1. Well, if I want to compute this point here, what I can do is take the tangent at xi, go a bit in the direction of xi plus 1, so that's this delta x here. That's a first order approximation, so if you just consider everything up to here, that's the first order approximation. You expand further, you have the second correction term. It depends on the curvature, not only the tangent, but the curvature. Then you get a third order approximation, which depends on, I think this is called Corsiosis, and the fourth, and so forth. And so I will stop at the third one and keep all the other terms in just as an O of the fourth order. And remember, like delta x, we think of delta x being small, not 10 or 1, it's like 0.1. So this here is a really, really tiny number. Okay, but in principle, like if you would continue and really get the fourth derivative plus fifth derivative and so forth, you could play this game, well, a lot longer. But as we will see, that fourth order will suffice. Now I can do the same thing, but now I can compute. And it's also clear how, by the way, if we still look at this first formula, it's also clear how this will be a given approximation of the derivative. So if this here is what we want to compute, we just put this on the other side, take the f of xi plus 1 on this side, divide by delta x, and we have an approximation of the derivative up to very specific higher order terms, error terms. Yeah? So that's what, remember, that's what we were set out to do. Approximate the true derivative by discrete derivative. Now we can do the same thing, and now it's not clear at all why I would just write the same thing twice with xi minus 1. Yeah. So xi minus 1 is again fx of xi minus the tangent, or tangent in the direction of from xi to xi minus 1. Again, plus second term, minus third term, plus higher order terms. It's not interesting, right? It's the same thing. But there's an interesting or kind of surprising advantage of doing both. Yeah? And that we will discuss first. Right now, so the first line is really what I just said. That follows. So if we say we call this 1, we call this 2, yeah? Then 1 implies this, 2 implies this. Everyone, I hope everyone sees it. If not, I mean, it's really just really trivial algebraic reformulation. Put all the terms that on the one side and all the terms on the other side. Divide by delta x. So here you only have a delta x, not delta x squared. Here only delta x squared. Same for here. The only difference is actually that here instead of x plus 1, I plus 1, you have I and I minus 1, and here you have a plus instead of a minus. Now, so why did we do both, and what's the third line? Yeah, okay, it's written already in the conclusion. So what you can do now is actually the both right-hand sides. So this one here and this one here are equal to the same thing that you want to compute. Now, what you can do as well, like let's call this here A and this here B. Yeah, so we have seen the derivative of f of xi is A is B. So what I can also do is A plus B half. The magic thing when we do that is the following. Yeah, here, okay, the xi cancels out because I have minus xi plus xi, so here it's just the difference of the neighboring points, not the point itself. But here, what happens? I have the same term but with a different sign, so it cancels. What that means is, well, this first order error term, if I just use this here as an approximation of, this is my discrete derivative, then here I will have an error between the discrete and true derivative of order delta, same order delta square. So this here is a much better, this averaging over the neighborings only is a much better approximation of the derivative than just the naive going to either the left or the right. Now this is not just like being pedantic, but really like if you set up your grid, the solution as well, I try to explain like it depends on the, say the error depends on the length or the size of the increments in general. Like here it will depend on the size squared. So what it means is it's a really big difference. So for instance, if you set out your algorithm based on the first equation, in order to reduce the error by half, you need to increase the sample, not the sample size, the discretization by a factor of 2. So instead of, say, 10 points, you need 20. If you want to cut it by 10, you need to multiply by 10. Yeah. If you multiply by 10, instead of 10, you have 100 points. This error will be cut in 100, not in a 10. So you need like significantly fewer points in your grid, and points mean like computational time. Yeah. So it's this kind of, or this trick is really very important for performance of the method. Not really for the understanding of the problem, but okay. Yeah, so we can also do that with the same second derivative, exactly the same story. We take both neighbors minus the center, twice the center. It gives us an approximation of up to second order. And now we will use all of these approximations exactly in that grid. So where we had the equation was delta V is something depending on delta XV plus something depending on delta XXV plus something depending on V. That is the Black-Scholes equation. Yeah. So in order to compute, say, this value, we will do the same idea as in this Euler scheme for the ODE. We will use this point, but now we also need all these gradients. And we will just replace them by discrete gradients, the ones we've computed now. Yeah. Okay, so that's just the formalization. So as I said, I will always consider this reparameterization in time going like maturity or terminal conditions become initial conditions. NT is the number of spacings in time, like how fine my grid is. NS, the spacings in space, so in this S coordinate. S min and S max, yeah, the boundaries of my universe. And what I will do is I will use the following notation. For the solution, or the numerical solution actually, I will denote V upper index k, lower index j, the solution at time tk, given state Sj. And so in this picture, like I think it's much simpler to just look at this picture. So here I have this point should correspond to, maybe I change the color. So this point here is V00. This point is V01, V02, etc. This point, for instance, is V10, and so forth. V03, V11, and so forth. Okay, and one thing to notice straight away is that, well, what we know, simply because we know the payoff function, is this whole line is known. So the 0th row here is V0J. No. Good. Well, so the task, what we want to do is compute these values here, because those are the price at today's price. Mainly. Also, well, the hedging strategy, which is the derivative of V. But let's focus mainly on the price now. So how we will set it up is really following exactly the idea from Euler for ordinary differential one-dimensional equations. Yeah? I have the derivative here. I replace it by this discrete derivative. So k plus 1 is the... You just need to get used to like upper indexes for time, lower index for space. And I will replace all of the derivatives that appear here, so this one, by the formulas that I've derived previously. So obviously I'm going to use the best one. So the not just left, not just right, the midpoint one. Yeah? So this was exactly here. I'm going to ignore all of these terms, and the derivative will just be approximated by the first term. Okay, now one crucial insight. This is a linear, so I mean all of these terms I know. Vk is known. I start with V0, I compute V at 0 meaning the upper coordinate. I compute V1. So all of these terms on the right-hand side are known. And I can just compute V1 simply by adding to V0 delta t times this right-hand side. Exactly the same principle as we've done in the Euler, discrete Euler. Now, a further thing to notice maybe is that you can bookkeep all of this in a neat form, because this equation is linear in V. Yeah? It's multiplied, but all of this is linear, so you can collect all the terms with just j, all the terms with j plus 1, and so forth, to arrive at this form. So I'm not going to do the calculations, but this is really just collecting all terms. If you're skeptical, we can also do that, but like I think, yeah, exactly. Okay. So that's it. So you can collect all these terms in a matrix, yeah, M, and not just compute the indices by itself, but just compute the whole vector by matrix multiplication. And an interesting thing to observe is that this matrix M is sparse. Yeah. Why is it sparse? Well, because in order to compute the point J at state J, I only need the neighbors. So it will be a matrix that is has the diagonal and well, one to the left, one to the right. All others will be 0. Okay? So it's a sparse matrix. Okay. That gives you an algorithm. You start V0 that is given to you. That's the terminal conditions. V0 is just filled up by the terminal condition or initial condition, terminal condition, depending on parameterization of time. You compute V1, the first row in this picture. You can compute this first row. Oh, the mouse isn't working, okay. And you go further. You compute the second row, third row, to the final row. Now, okay, no obligations. I've cheated, or I didn't explain to you the full story. So why does anyone see what we've left out so far? If you, yeah, exactly. So what we can do is this formula, what we have here, right, to compute vk plus 1 requires vk at j minus 1. It's a linear combination of these three. So I can write this maybe more graphically. So if I want to compute this one, I have this one, this one, this one. A linear combination of these three guys will give me the next number. Now, but what happens? So this one I can compute, this one I can compute, this one, but this one, there's no neighbor in the previous row to the right. What I need is extra information. And this extra information comes in terms of the boundary conditions. At the boundary, you need the boundary conditions. We've seen two types of boundary conditions, I think, or three. Two. Dirichlet and Neumann, for sure. So if you have Dirichlet conditions, those are exactly describing the value here. So this will be via boundary conditions. For Neumann conditions, it looks slightly more complicated because those were not pertaining the value, but the derivative, the slope. So what for Neumann conditions you need to do is, or one approach is to introduce like an extra line here that you fill out. But like, if you understand it for Dirichlet conditions, you're perfectly good to go. Yeah. So first, yeah, just think of Dirichlet conditions. Okay. So at the end of today's lecture, we will come back to the case study from last week. What was it? Some out and in options, and see how you fill up these boundary conditions concretely in the grid in those examples. Because if you're interested in doing the fourth exercise sheet that I will be handing out like tomorrow, you will be required to exactly like do that. Fill out this grid, construct the grid, fill it out, build the algorithm, and so forth. Okay, so this is just a recap of this explicit, what is called explicit scheme, explicit forward scheme for this type of PDEs. Yeah, so okay, it's really similar to this backward induction in some sense. It requires, like, the computational power or complexity is roughly quadratic in the number of spacings. You have these initial conditions, you have boundary conditions in form of Dirichlet, I think. And the error, we will not prove this at all. In the second part of the lecture, I will be talking a bit about stability and convergence, but briefly only. But the error, as you can imagine, like all the terms that we've neglected were of order delta x square, and we've just done a forward step in time. So what you can imagine is that the error is like roughly behaving like that. And you can prove that. Yeah? So we will not be able to prove it. That's really beyond the scope of this lecture. But you can prove that this algorithm converges at exactly this rate. And that's sharp also. So it means if you want to be accurate to a certain degree, you need not so many points in space, but quite a lot of points in time. Okay, so this was the first method that I want, or that we will see today. Yeah? It's the easiest one, and it's somehow hard to imagine that there are other methods as well. But I will discuss two more methods after the break, and well, in the second part, like in half an hour or so after the break, or after now, also discuss their weaknesses and strengths. Yeah? So each of these methods will have some advantages, some disadvantages. But now you've seen the first method to really discretize these PDEs that really converges at a specific rate. So that's already quite a cool accomplishment for today. So that's, I think, a good place to make a stop for, say, 15 minutes. Return at, or resume at 2010. Welcome back. So one tiny comment. So this here is not plus but minus. And just if you were confused, that's a typo. It really doesn't matter. We neglect these terms anyways. All these terms in our approximation. But yeah, just if you were confused. Now, okay. So what we've done so far, I hope it was not too difficult actually. Yeah, we've just taken this idea from Euler. If I have a solution, u prime t is f of ut. What I can do to construct a numerical solution is u tilde t0 is just u t0, and u tilde tk plus 1 is u tilde tk plus f of u tilde tk, delta t, which recursively gives me the value. And what we've done is added a layer of difficulty where u not only depends on time but on space, and we've used discrete derivatives to approximate the derivatives in the PDE. Now, I would guess that if, depending on your exposure to math and differential equations, if I would ask you to come up with a numerical scheme for ordinary differential equations, you would come up with this one. Maybe in a minute, maybe in an hour, but you would come up with this one. It's the most natural idea. Yeah? So now why did I tell you that I will explain 3 solutions, 3 different algorithms? What could be another algorithm to consider, given that this one is so natural? It's somewhat hard to picture that there should be a competitor to this algorithm, even for this for the classical, this ODE. Yeah? But what you could also do is, remember, I mean, the idea was the following. The true, or if you formalize the idea here, is that the true solution, utk plus 1, satisfies utk plus tk plus 1 f of u of s ds, and we've approximated this unknown, well, if we just know utk, this unknown integral by the left-hand limit. But in fact, we could take any value. We can also take the right-hand value, in principle. So what we could also do is we could set up a scheme as follows. Alternative scheme. Alternative scheme. utk plus 1 is the numerical solution is utk plus f of u tilde tk plus 1 delta t. The difference here being that I take the approximation using the right-hand limit. And this is what will turn out to be the implicit scheme. Implicit, well, because it's not as explicit. Here I can really walk recursively along my grid. Here just the spacing. Here it's not so clear. Like if this function f is very complicated, it's a priori absolutely not clear that this even has a solution. No? And even if it has a solution, if someone guarantees you that it has a solution, it's still significantly more complex. I mean, what you need to do is, you need to essentially solve for some number u that satisfies u is u tilde tk plus f of u delta t. I mean, if f is nice, linear, for instance, it's not difficult. But if f is an arbitrary function, it may not be as feasible even. Yeah? So this sounds like a stupid idea. Well, just on the face of it. But it turns out it is not. So this implicit scheme, if you run it for the PDE, it has exactly that form. So one increment in time. What I use to discretize my derivative is I use the unknown function. And remember, so we know vk, we want to compute vk plus 1. So that's the whole game. Just to make this very clear, the comparison here for explicit is I only use values that I already know for the right-hand side. Very reasonable. Here I use the values of the right-hand side, which I add at a future step, which I don't know. Now, fortunately, it still doesn't look so bad for us here, because again, this is linear in the right-hand side is linear in V. So I can simplify things, and if you compute, if you take all these vk plus 1s on one side and the vk's and j's on the other side, what you will get is this equation. Yeah, so an equation for vk plus 1, where now all the vk plus 1s are multiplied by certain constants that follow just from algebraic reformulation of this equation. And in matrix notation, again, you set up a sparse matrix M, where in the diagonal you have in the diagonal you have C prime, apparently. And in the two off diagonals you have A and B, sparse matrix. But now the matrix is multiplied on the unknown. So previously what you had to do to obtain the solution, vk plus 1, is just matrix multiplication of vk plus p. Now what you actually need to do is solve a matrix equation, and you can reformulate this. As vk plus 1 is equal to m minus 1 of vk minus p. Given that m is invertible, of course. It turns out m is invertible in our example, so that's fine. Still, it's much more complicated. Like there are two views on this. So one view is, well, you need to do a matrix inversion, which is in general quite costly. So this is not a simple, like numerically inverting a matrix is not for free. That will cost you time. The other approach to viewing this is, well, this equation actually tells you that you cannot solve for every vk plus 1 of a fixed j. You need to solve for the entire next row simultaneously. You need you cannot just localize the problem, going one column up, but in each coordinate separately. You need to solve for the entire row. Maybe if we look in this picture here, so the implicit Euler scheme, maybe that is green, it takes the following form. So if I want to compute this value here from previous ones, I need this one, and this one. all of these will give me that one. But, well, the left and right neighbors are also unknown, so I need to do it simultaneously. Yeah? So geometrically in this graph, it just looks very different. Okay, why would you do that? So any advantages so far? Doesn't look like it. We still have this error, the same error, because we've approximated differentials in S by the same differences. We just did one step forward in time. Same error. We need to invert this matrix at each step, but what will turn out that this is just much more stable, numerically stable method for this type of PDEs that the Black-Scholes PDE, or of this Black-Scholes type PDEs. So I would, in 2 slides, we will discuss the stability. So the price here is that it's computationally much more expensive, but it's this method that is much more suited to the structure of the PDE that we are given. And we will see, I will discuss why. Now the final method is, well, you can imagine maybe what we've done so far. We've averaged the left neighbors, the derivatives computing by the left neighbors and the right neighbors, got an improved error. You can do the same thing here. It's called Craig-Nicholson scheme. So it's exactly this. Yeah? You average. So this here, the lower part is the explicit scheme, so the forward scheme. That would be, if you just have the lower part and forget that there's an upper part, just this one, that is one step in the explicit scheme. If you just consider this upper part, it's one step in the implicit scheme. Now you compute it using an average of those. It turns out that here, as in the previous, as in the derivation for derivatives, that will improve the error. Yeah? So the disadvantage is, again, of course, I mean, you compute the unknown bk plus 1 using the unknown bk plus 1. So it appears on both sides, and it truly appears so that it will not cancel out magically. So it really is there. So it's an implicit, again, an implicit type scheme. You need to invert a matrix and so forth. The matrix looks more complicated and so forth. Like all of these negative aspects, it inherits from the implicit Euler scheme. But what it does is, well, as we will see, it inherits also the stability. So this one is really well suited to equations of Black-Scholes type. Plus, it has this much better performance, this error performance. So again, that's a huge difference because, like, now I mean, your grid can be significantly coarser, and you still get like very good approximations. So that's actually also why, if you consider like many solvers, built-in solvers for PDEs, would be built on Craig-Nicholson, a Craig-Nicholson scheme. Yeah? Nevertheless, like, you will not be asked to implement this. This would be a bit too cruel, maybe. And you will implement implicit and explicit Euler scheme, and that's it. Okay, so far so good. Any questions? So this is where I would stop with the algorithms, like the construction of the algorithms, and I will discuss briefly why we have 3 different algorithms, what is their behavior, what is their disadvantage in particular. I'll give you the reason why we didn't just use explicit Euler and that's it. Okay. So now this is what I call stability and convergence, actually. Convergence we will not do as rigorously as stability. So there are two concepts here at play simultaneously. Convergence is, well, how fine do I need to make my grid? And I've indicated many times that, for instance, the error is like order linear in the time discretization, quadratic in space. Craig-Nicholson was quadratic in both. Yeah, that's convergence. So how fine does my grid need to be to get a certain approximation? And stability is more concerned with the question, like broadly speaking, if this method and the PDE that I want to apply it for, because like this method, like it doesn't require Black-Scholes. You can do the same argument using any kind of PDE. Yeah? Whatever PDE you have, you discretize time and space, move one step, for instance, in explicit Euler forwards by computing discrete derivative. An arbitrary PDE you can discretize that way and solve numerically that way. And numerical stability concerns with the question is that method compatible with the PDE we're facing? And if it's not, typically you need to be very careful if the specific parameters are chosen correctly and so forth. Yeah, it's very unstable. Right. So this is, discretization you have. And mathematically what happens is like discretization induces some form of error. Yeah. And this error just doesn't stay constant. In each iteration step, you remember we calculated forward and time, say, bk plus 1 from bk, vk plus 2 from bk plus 1. In each of these steps, you introduce another error that is built on top of the previous error. So somehow the errors in principle could accumulate and have some form of compounding effect. And if that happens, then you need to be quite careful. Then that could indicate that the solution is not really too stable if all the errors amplify. Okay, we will not do this too rigorous. It's more important that you understand the concept rather than like I will not show you any like real proofs or anything like that. Also, this is like not a simple topic. Like there are courses on numerical aspects of PDEs, entire courses where you discuss these type of topics. Yeah. But nevertheless, what we're going to do is we're going to consider just a toy example. Yeah? We were interested in PDEs, specifically the Black-Scholes PDE, numerical solution to that. What I'm going to do is instead, I'm just going to consider like this basic idea of implicit versus explicit just for this ODE. Keeping in mind that we're actually doing PDEs, but just for the sake of like presentation, consider this ODE. And to make it even more simple, I will consider a linear ODE. Yeah? So we all know what the solution is, right? So the solution is just ut is e to the beta t. Say if u0 is 1. Yeah? And finally, I'm going to restrict myself to beta smaller than 0. Beta is negative. Yeah? So what happens is that the solution is decaying exponentially fast. That's in stark contrast. So typically when all the exponentials we had were positive, like returns, time t, we had a growing bank account. Here we have something decreasing. And that's the example I'm going to consider. Now, surprisingly, what turns out is that this is actually not really a toy example. This is a simplified but still highly informative model. And since like when I read this type of stuff, I was wondering, so I will show you why this, typically the analysis is carried out in this very, very simple model. I'm going to give you the maths now in one slide. I'm write the maths down for a couple of minutes. The disclaimer is that don't, like if you don't understand it, don't worry. Like it's not going to appear in any exam or anything. Yeah? It's just for those of you who might have a math background to make sense of this. And if you don't have a math background, then view this. Yeah, don't care too much about the details. Okay, so what we have is what we consider is only ut is ut delta t is beta ut, and beta was negative. So that's the model we consider to analyze stability. Now the model that we're actually interested in is Black-Scholes. PDE, yeah? Not ODE. And what we've seen, so like last time, and I've mentioned today many times, is that this actually, using a transformation, an increasing transformation actually, is equivalent to the heat equation. And the heat equation, how does it read? Delta T, let's do W. Tx is, okay, there was a factor of 1/2, which I'm going to ignore, but it has this form. Yeah? Derivative in time is the same as the second derivative in space. That was the heat equation, right? If you don't remember, that's given. So a function that depends on two variables. Now what you can actually do is the following. Now is where the maths comes in. So define this operator L, which goes from smooth functions to, say, smooth functions. And it maps a function to its second derivative. Yeah. So L is an operator, so linear mapping from this infinite dimensional space of smooth functions to the space itself. I take a function, I differentiate it twice, that's what L outputs. So L outputs a function, takes its input as a function, outputs a function. Yeah. Now I claim this operator is linear. Oops, L goes from 0. Yeah. That's a linear operator because, like, if you have two functions, you add them, you differentiate the sum, it's just the sum of the derivatives. Same for the second. And it's also homogeneous. Yeah? So L is a linear operator. Now, what can I do is I can delta T, W delta T dot, I can write it as L of W T dot. So I fix my time component. If I fix my time component, W is a function of X. So this here is a function of, say, a smooth function, and this here is a function. Yeah. I apply this operator to this function. And what I get back is the second derivative. So this is another way of writing the heat equation. Yeah. The semi-group way of writing the heat equation. Okay, and what do you see? Like, it's actually a very similar form. It's very similar form than the ODE that we considered. Yeah? If I write this dot here, I mean, actually, I shouldn't probably, but... So in one dimension, a linear operator is just a number, a multiplication by a number. That's the only linear operator you have. This is just in high dimensions, and in general dimensions, you have a linear operator. So you see, actually, our PDE is nothing but like a very complicated ODE, but a linear ODE in very complicated spaces. And what is missing is why is this condition that this linear operator, this number, is negative? Yeah. This you can also verify. Yeah? So this operator, this Laplace operator, L, so the concept of positivity or negativity in vector spaces is you define it by like eigenspaces, eigenvalues. Yeah? And what you can verify is like if you have phi k is, for instance, sine pi k x. So that's those are functions which span the whole space. So those are the analogs of, like, in Euclidean spaces, you would have unit vectors, so 1, 0, 0, 0, or 0, 1, 0, 0, 0. Those functions phi k are just the analog to that. If you compute the Laplace of phi k, then that's just minus pi k square phi k. This is negative. So this implies L is, or this is equivalent to L being negative. Okay, so the main message of this slide is this toy example, ODE with linear ODE with negative coefficient is a simplification, but a minor simplification of the actual model that we're interested in. So Black-Scholes really very much behaves like this ODE. And again, it's not at all important that you understand this, what I've just told you. It's really like I wanted to show you because I would be like dissatisfied if someone would just tell me we consider this trivial example instead of our PDE, and that's going to explain everything. It's just that you have the information if you want. If not, take this as a given. That's totally fine. Okay, so back to our example. U is just an ODE, linear ODE, negative beta, and we're going to analyze all the different methods that we had using, or just on this ODE. So the way we do it is, okay, if I have the true solution U, and UK plus 1, or UK is just restricted on the grid, yeah, then it will satisfy this equation. What does it say? Well, UK plus 1 minus UK divided by delta is, in principle, I have an integral here. That's what I showed you on some of the handwritten slides a couple of minutes ago. I discretize, or I approximate this integral by the left limit. I will have a discretization error, which will be of order delta t. I will still continue write the delta st, but because that will be if we apply all of this, or if we would apply all of this to our PDE, then that's the error that we would get in each step. But it's a delta t error here. And what I can do is I can write this as an iteration of explicitly UK plus 1 as UK times this factor 1 plus beta. And this here we will always call G, so that's a G, not 6, G as a growth factor. up to, of course, this discretization error. Now, the numerical solution in forward Euler was exactly like ignoring this unknown discretization error. Yeah? So you've seen you have also recursion for the numerical solution, the same growth factor. Now what you can do is, maybe I can make it big. What you can do is consider the error between true and numerical solution. Now, both of them satisfy the same dynamic. One has a discretization error, one has not. So if I calculate the dynamics of the error, it will witness the same behavior. Error at k plus 1 is growth factor. So okay, again, that is G. Growth factor multiplied by the previous error plus a new error. And now what you see is that all these errors accumulate. They intensify. Like, I mean, they get multiplied by this error. So error maybe 3, let's do it for 3, is error 2 times G plus discretization error is error 1 times G plus discretization error times G plus discretization error, so and so forth. Yeah. So all of that, okay, here's a -1 actually. This is -1, and this is -2, and so forth. That doesn't matter. But like what you see is that this final error at the final step, and that's what we care about. I mean, in our example, that was the initial price. The error for the initial true and numerical initial price. It will be multiplied by this growth factor to the power of n or n minus 1 or exponentially in any case. So what happens if G is 1, then nothing bad happens. Yeah? It's just 1 to the power of n, it's okay. But what if G is, in absolute values, larger than 1? Say G is 2. Yeah, and remember, n was not some small number. N was large because the grid was fine. We know the error scales like 1 over n. So if I want a small error, n is maybe 100, 1,000. N is a large number. Say G is 2. I have 2 to the power of 1,000. That's like an astronomical. That's an incomprehensibly large number. So what it means, the error will be extremely, extremely bad. So what it means is that this solution, this method, is not really applicable or not really stable if this factor G is larger than 1 in absolute values. I mean, if it's -2, it's the same principle. So G in absolute value has to be smaller than 1, and well, that requires that beta times time step is smaller than in between -2 and 1. So that is equivalent. Remember, beta was negative in our example, so delta t has to be smaller than 2 over absolute value of beta. Yeah. So that is a parameter that you need to really be aware of in your modeling. If you consider explicit Euler for these type of equations, you need to really make sure that the time steps are really, really small. And for Black-Scholes, I mean, yeah, Black-Scholes, let me write this down. Black-Scholes is like delta t, it has to be smaller than some constant times delta s square for this to work out. Remember we had, I mean, it was this operator L, you need to compute what all these eigenvalues are essentially and so forth. And that is the requirement for explicit this Euler scheme in the Black-Scholes model to be stable. Yeah. So many time steps, yeah, in comparison to your grid actually. Okay, now you can also plot this solution, and the true one is the blue one. It starts at 100 for whatever reason. Yeah. Doesn't really matter the value exactly, but that's the true solution. Now, if you do maybe just 4 steps, so that's a very coarse approximation, obviously. Just partition into four pieces. But nevertheless, you will see that the numerical solution for 4 steps is, well, horrible, but also it just behaves very, very differently. The structure, it looks very more like a sine or whatever than an exponential. And even if you increase the step size, no, not the step size, if you increase the spacing, so reduce the step size to 6 or 12, it will converge because we've seen the convergence rate. It will still converge as delta t goes to 0. At the same time, it still doesn't really respect the structure of the solution. And it converges quite slowly. Like even for 12, you still have a significant gap. That's like maybe 30% off, which is quite a lot. Okay, so this was the explicit Euler scheme, and that's the downside of the simplicity. Yeah? It's just not suited to this method. What happens for the implicit scheme? Same argument. So I expand the true solution, discretization error. This time I'll compute the integral via the right-hand approximation, not the left-hand. For the true solution. For the numerical solution, that's exactly what my algorithm does. So that's the definition of the algorithm, to take the unknown for the right-hand side of for the derivative. Again, I have this growth factor g in both models. I expand. I consider the dynamics for error between true and numerical solution. Yeah. I get the same dynamics for the error, but now this time the growth factor is on the left-hand side. That's the key difference. So here, the iteration is epsilon k plus 1 is 1 over what we had previously as the growth factor. And if you do the same thing, like this amplifies, the leading term will be like delta t times g to the power of n. But now what's the magic? Actually I can erase all of this for us. So beta is smaller than 0 in our example. So in the setting that we're interested, beta is smaller than 0 for Black-Scholes. So what is this number? Delta t is positive, beta is negative. So g will always be g smaller than 1 always. Yeah? So regardless of the step size, regardless of the value of beta, I don't need to be careful about any of those things. It will always be stable for these type of methods, for these type of equations. Yeah? So this is what you would call unconditionally stable. And also, if you actually like plot numerical solutions, and of course, I mean, these are interpolations of the solution. I mean, again, I have 4 to 12 time steps. You see, well, firstly, it converges quicker, but also it looks like it respects the structure of the equation itself, or of the solution. Okay, finally, Craig-Nicholson. The difference here, it's just more complicated to write down. Another difference is this discretization error is now order delta t squared, not delta t. Yeah, but still, like how it's built is. Yeah, I mean, I can really do the very same thing. Like here, I approximate this integral not by the left, not by the right, but by half left, half right. Write down the formulas. Write down the formulas for the numerical solution. Yeah, really exactly the same thing. Compute the dynamics for this error term and find that this error term, again, this is G, of course. So the growth rate at which the error amplifies in each round has this form. And again, if beta is smaller than 0, this will be always smaller than 1. Yeah. So you see the clear winner, at least from stability and convergence, is Craig-Nicholson. It's fast. It has no parameters that you need to be specifically careful about. It's computationally a bit more costly, but that's a price. That's a small price for all these benefits. So that's why all the solvers for these methods typically use Craig-Nicholson. Otherwise, I mean, they would need to ask you, like, hey, what do you think is beta in your case? What's the step size I need to choose, and so forth. Right? That's Craig-Nicholson. So you see, like, rate of convergence is much, much faster than in if you compare it to implicit, or explicit as well, of course, but implicit even. Looks a bit, yeah, not as nice as implicit, because like it also has this implicit component. But still, like it doesn't blow up, and it converges fast. Okay, this is all I wanted to say about these numerical methods. Yeah. So now you're capable of, hopefully, of implementing parts of this at least yourself. That's what you will be asked to do in the problem set that I'm going to upload tomorrow morning probably. You should at very least, again, some of the maths that we did today, forget my slide with this operator. That was just really I don't know, just my curiosity. But what you should be able to, or what you should take away from this course is not only the algorithm, but that there's different algorithms, different advantages, different disadvantages. At least be aware of this for sure. Yeah. Yep, let's, for the next 10 minutes or so, let's close this lecture by going back to the case studies for the Black-Scholes PDE in different type of options, really pin down the boundary conditions, We did it last time. Let's repeat that. Really write down the values in our grid that we set up. So this will be so essentially like part of your problem set. Like if you follow this, then you have part of your problem set essentially solved. Yeah? Okay, so same slide as last time. We have up and out call option. So terminal payoff as terminal time VTS is there's a strike, there's a barrier. The payoff is 0 until you hit the strike, 0 if you hit the barrier. Yeah, we have seen we can compute both Dirichlet-Neumann conditions for this example. No problem. And maybe to make it concrete, so let's say that, again, S is like 100, volatility is reasonable, like a couple of percent, K is 120, B is maybe 150. Yeah, so these are my values, 120, 150. And how do we set up our grid? And our algorithm? So time, there's just a discretization of time. I'm going to again do it with time reversal. So here's t and here's 0. And I know initial conditions. So the first thing, okay, there will be some like delta t that we need to choose, whatever that might be, small. I need to specify as min, as max. In this model, maybe S min could be something like 60. The chances that log normal goes below 60 are astronomically small. Maybe S max is something like 180, maybe a bit higher. Yeah. And so here's maybe 60, 70, 80, 90, 100, 110, 120. Okay. Well, 130, 140. It's not the best picture. 150. Okay, let's actually do 160. So this is now S max. 60, 70. Okay, equidistant. Think that those lines are all equidistant. And of course, like it's a very coarse approximation. You would have something much, much finer. Now, what are the conditions that you can already, without thinking, specify? 0 on both hands, exactly. So here you have 0, 0. You mean this, or you mean really the whole thing should be 0, exactly. So those are the Dirichlet boundary conditions. Yeah? So remember how did they emerge? I'm going to just explain that once again, because this is really the part that you actually need to be like problem specific. Everything else is just the algorithm, but setting up the boundary conditions, that's sort of the engineering part in this aspect. So the value here, what does it represent? Or say, let's start with this value here. So 0. Here it's clear that it's 0, because if at maturity stock is at 60, your option just doesn't activate. But this number here is, say, like, you have the option expires in a year. This is like in 11 months. So at month 11, stock price is at 60. Your option in 1 month only pays out if stock price is going to jump all the way up to 120 or higher. That's extremely unlikely. So if you were to sell or buy this option, you wouldn't pay a lot for it, right? It almost has zero value. And if we think like that S-min is not just 60, but really like 0, then it really has zero value. Yeah? So it's roughly 0, but we're going to stick with 0. And the same for here, because even if today or at month 1 the price is 60, still there's really no chance that it's going to explode with 2 or 4% volatility all the way up to 120. Now, same reasoning here. The reasoning here, again, being that, okay, we have this barrier also. Like if we hit this barrier, so if it exceeds 150, then that option again deactivates. So maybe 180, we could have picked a bit something slightly higher, but whatever. Yeah, so again, 0, 0, 0, 0. What else do I know? Always, without any engineering, I'll always know the first row, the bottom row, because that's the payoff at maturity. And so here, again, I know it's 0 because the option doesn't activate. 0, 0, 0. Still 0, okay, I'm in the money, but I'm exactly at 120, so 0. 130, I'll get paid 10. 140, I get paid 20. I hope you can see it. If not, then it's 20. Now at 150, what happens at 150? 0, or it depends on, well, it depends on if you need to exceed the barrier or if you need to be smaller than the barrier. Here in this definition you need to be strictly smaller, so 150 would be just the cutoff. It's again 0, but like if it would be smaller or equal, again you would have 30, again 0, 0, and that was 0 in any case. Yeah. Now if you would do this grid finer, you would see, this part here. You would just have a more increasing function, not just 2 values. And that's all you need. Now you can really run your whatever algorithm you wanted to run. Say the forward algorithm, for instance. So in order to compute this here, you average these zeros linearly, so it will again be 0. Yeah? So, but I mean, okay, you don't need to do this by hand. The algorithm will do it. Yeah? This you can compute and so forth. You can go all the way up. Okay, so this was the up and out. Up and in looks very much similarly. So what do I have? Okay, this option I have K, again 120 maybe, B 150. So it only activates, it's 0, 0, 0, it activates here. And yeah, that's it. So it looks very similar. Maybe let me, so this was up and out, right? Out and, nope. What did I do? Okay. Let's write it in orange. Okay, clearly this first row I don't need to write this first row. Like everyone knows, right? So the first row, this is fine. That's just reading off the value of the function itself. Left-hand value is again 0 because it has less value than a call option with a given strike price. So this value will also be 0, 0, 0, 0, 0, 0. And the right-hand side, what happens at the right-hand side? So think about like this scenario, you're 1 month before expiry. 180 is maybe a low number. Think it's very, very high. Stock price is at 1,000. Your option pays out stock minus strike K if, as long as you're larger than the barrier. You're going to be larger than the barrier. Like there's almost no chance that you're not. So what you're going to pay for the option. Okay, so here will be S. So what is it? 100, 800 minus K. Almost. Like think that this term wouldn't be here. So if in a month I tell you in a month I'm going to pay you K, discounted. Yeah. So e to the minus r delta t, right? Yeah. Yeah. So and similarly with all the other values. So again, here this would be 180 minus k e to the minus r 2 delta t, and so forth. T probably. Yeah. And again, and 180 is maybe a bit small in this context. I should have picked something larger, but maybe 250. I think that's it. So this was PDEs. This was numerical methods for PDEs. We could also discuss like Neumann conditions for these methods. At the same time, like for all the options, you can easily write down the Dirichlet conditions as we've done now. This is a bit simpler, so let's stick with that. Implement it with Dirichlet conditions. If you think about Neumann and don't figure it out, then we can discuss this next time as well. But for now, let's stick to the simpler solution. And that's it for today. Next week we will do the preliminaries for the statistical analysis of these equations, statistical solutions of these equations later on. That's going to be next week. But yeah, that's it. See you next week.